Okay, let's just dive right into this. Welcome to this explainer where we're going to demystify the completely opaque black box of algorithmic credit approval. Look, we interact with these invisible automated systems literally every single day of our lives, right? Usually without even realizing it. But what actually happens when the math goes wrong? Today, we're going to break down the anatomy of an algorithmic failure by looking at a fascinating and frankly, a pretty frustrating real-world case study. We'll unpack the whole shebang, the data science, the math, and the human decisions that caused a machine to make a completely illogical choice.
Section 1. The 2022 Loan Rejection.
So back in 2022, there was this group of young, really successful online entrepreneurs. They applied for a standard business expansion loan, and honestly, they were expecting an easy approval. They were doing great, looking to the future, doing exactly what any growing business does to scale up their operations. But they got denied. No way, right? Why on earth were these seemingly perfect applicants rejected? Well, it turns out there is a massive, often totally invisible gap between human common sense and machine logic. See, when a human looks at an application, they read a story. When a machine looks at it, it just sees isolated data points. And in this specific case, the machine's translation of those data points was fundamentally broken.
I mean, on paper, these folks were absolute dream candidates for any bank. They had a steady, incredibly consistent income stream rolling in from their online business. Their credit history was completely clean. We're talking zero missed payments, zero defaults. And they came armed with solid, highly verifiable references. Seriously, if a human loan officer had just glanced at this file over their morning cup of coffee, they probably would have stamped it approved in, 5 minutes?
But instead, they got hit with this shocking conclusion. They were officially labeled as high risk by the bank's automated system. Boom. Application automatically rejected without a second thought. So you really have to ask yourself, how does an algorithm look at a practically perfect financial track record and somehow see a high-risk gamble? Well, to figure that out, we need to take a look under the hood of the technology itself.
Section 2. Inside the banking algorithm. You see, financial institutions lean really heavily on statistical learning to predict credit risk. The whole goal is to decrease their losses and accurately predict a client's future business performance. And one of the foundational tools they use for this is multiple linear regression. At a basic level, algorithms are essentially just trying to draw lines through historical data to separate the good risk from the bad risk. When you've got multiple predictor variables, stuff like income, age, credit history, the algorithm tries to find the mathematical relationship between all those inputs and the response you actually care about, which in this context is the probability of them defaulting on a loan. It's basically trying to fit a line, or a geometric plane, through this massively complex scatter plot of human behavior. For instance, think about a model trying to predict credit card balances based on income, but it separates people into groups, like students and non-students. What the model does is fit parallel lines to the data. It calculates a different starting point, or an intercept, for each distinct group, but then applies the exact same slope for income across the board. And honestly, this is exactly what the bank's classification system was doing to our young entrepreneurs. It was just dropping them into a predefined, rigid mathematical bucket based on a few specific variables, and then blindly drawing a line to predict their future behavior. Section 3. The zip code bias. But here's the million-dollar question. What happens when the model just picks the wrong buckets? To get why this is such a massive mathematical blunder, we got to talk about a classic statistical trap: confounding variables. Okay, imagine you run a regression analyzing data at a summer beach town, right? And you find this super strong positive relationship between ice cream sales and shark attacks. As ice cream sales go up, shark attacks go up. Does that mean eating a vanilla cone attracts sharks? Should we literally ban ice cream to save lives? Of course not. That's ridiculous. The missing variable there, the confounding variable, is the temperature. Hot weather causes more people to buy ice cream, and it also causes more people to go swimming in the ocean, which naturally leads to more shark attacks. The model just got totally confused by a flawed data connection. And that exact statistical trap, that's what caught our entrepreneurs. The bank's model heavily weighted their zip code as a primary predictive variable, because historically, that specific zip code happened to match an area with high loan delinquency. But here's the kicker. The model completely ignored their massive recent business growth, and it completely ignored their sales seasonality. It just assumed that because they lived in a certain neighborhood, they automatically shared the financial habits of past defaulters who used to live in that exact same neighborhood. It essentially redlined them purely based on geography. The zip code was acting as this deeply flawed proxy, just like the ice cream sales, while completely ignoring their actual individual merit. Section 4. ignored variables and seasonality. Now, you have to understand this wasn't just some minor oops kind of oversight. This was a fundamental structural failure of the model's training data. In statistical learning, if you don't actively measure a variation, the mathematical function physically cannot use it for its prediction. I really want you to just reflect on that for a second. If a model is structurally blind to basic human realities, like recent explosive business growth or the natural seasonal changes in an online store's revenue, how can we possibly trust anything it outputs? The cost of missing that context is absolutely severe. Human actions naturally generate seasonal effects. I mean, just think of retail spikes during the holidays, right? Furthermore, introducing new products can cause super rapid changes in business trends. Our young entrepreneurs were riding a huge growth trend that the model simply did not have the vocabulary to understand. And here's the danger. When an algorithm is blind to these vital features, it doesn't just throw its hands up and quit. No, it relies on whatever flawed heuristics it does have access to. In this tragic case, a zip code. Section 5. The imbalanced data problem. So you're probably wondering, why do data scientists build models this way in the first place? To answer that, we really have to look at the historical data these models are trained on. 99.99%. Let that number just kind of sink in for a second. If you're building a machine learning model to detect a rare event, say finding cancerous cells in lung x-rays, or detecting fraudulent credit card transactions, or, you guessed it, predicting loan defaults, most of your data is going to be negative. The vast majority of people simply do not default on their loans. Because of this, a model can achieve massive accuracy, literally like 99.99%, simply by guessing the majority class every single time. It can literally just say, nope, no one ever defaults, and look incredibly accurate on paper, while actually learning absolutely nothing useful about real-world risk. And this right here is exactly why imbalanced data totally fails us. Because the rare classes, like those loan defaults, are so drastically underrepresented, there just isn't enough signal for the model to learn what a true default actually looks like. If the model isn't heavily penalized for missing these rare events, it just treats all samples the exact same way. To minimize its error rate as lazily as possible, it prioritizes easy broad stroke assumptions, like, say, penalizing an entire zip code, rather than doing the hard work of learning the complex, individual realities of actual borrowers. It gets stuck exploiting simple, lazy biases.
Section 6. Fixing data preprocessing flaws.
Look, algorithms aren't these untamable forces of nature. They are built by humans, and it is the humans' responsibility to practice ethical data science to prevent this exact kind of automated discrimination from ever happening. Data scientists absolutely must actively fix these flaws before a model is ever deployed into the real world. Step 1. Remove discriminatory confounding variables entirely. If a zip code is clearly acting as a proxy for socioeconomic status, get it out of the model. Step 2. Mathematically balance the dataset. They can use techniques like SMOTE, which generates synthetic, mathematically similar examples of the minority class, to basically force the model to actually learn the boundaries of risk rather than just blindly guessing the majority. And finally, step 3, ensure you're actually including vital business context, like sales seasonality, so the model is evaluating true merit, not just geography.
As we wrap up this explainer, I want to leave you with one final thought to chew on. We've just seen how bad data preprocessing unfairly crushed the dreams of some hardworking young entrepreneurs back in 2022. But remember, regression models and classification algorithms are deciding who gets a mortgage, who gets a job interview, and who gets vital medical care every single day. If the data scientists behind those systems aren't rigorously selecting fair variables and properly balancing their datasets, how much invisible algorithmic bias is quietly affecting your life right now? It's a question we all definitely need to be asking. Thanks so much for joining me on this explainer, and hey, keep questioning the data.